Hello, Coach Owings here over at Frisco High School. We are onto 9.2, 9.1. Ms. Anderson did a great job introducing us to correlation, and we're going to expand on that with our Barbie bungee concept here. And let's just dive in. So here's the data from one of the groups. The group forgot to record their measurement for 5 rubber bands. So you may see that they have a blank there for 5 rubber bands, what distance is traveled. So we're going to work to try and figure out what that could be. So we're going to make a scatter plot and calculate the least squares regression line. So I'm going to open up Staplet. And we want to go to 2 quantitative variables. Our explanatory variable, just like we've had, is number of rubber bands. Our response variable is the distance traveled. And then we're going to use that data that we have over here. So 0, 1, 2, 3, 4, skip 5, 6, and 7. And the distance traveled, 25, 32, 41, 49, 55, 69, and 78. So we begin analysis, and we're given this scatter plot, and we got a nice blank right there. I'm going to capture this and throw it into my Cami, into my notes. Copy that. Throw it into my Cami, make it much smaller because I have no room for this. But you'll notice there is kind of that blank there for where x equals 5, where the number of rands equals 5. We'll zoom in on that later. And we want to calculate the least squares regression line. This is the line that best models the data, and we're going to write that equation on here as well. So on your calculator, you're able to type into L1 and L2. You'll type in the number of rubber bands into L1, L2. That's in Stat Edit. And then to find the least squares regression line, you'll go back to Stat, go to the right to Calc, and then I believe number 4 is lin-reg for a linear regression. On Staplet, we can just go down here. There's our correlation. Wow, that's a fantastically perfect correlation there. Hopefully you know why, because of the video we watched over 9.1. Thanks, Ms. Anderson. And we can click this button here to get the least squares regression line, and we see a bunch of other stuff popped up that we'll talk about later as well. So we're going to write down that equation. So let's go on back here. Let's change colors. Let's make it a touch thinner. So we have y, and we're actually going to call this y hat. And that y hat is going to be 7.464x plus 25.333. So that y hat there, we called y hat because it's not necessarily what values we actually have, but it means our predicted values, our predicted y values. I'm going to draw in there a little y hat as well, y hat. So what that tells us is it's telling us our predicted distance. So this y hat's our predicted distance, and this x variable is going to be the number of rubber bands. So y hat is telling us our predicted distance, and this x variable is our number of rubber bands. So the next question asks us to use that regression line to predict the distance that Barbie travels for 5 rubber bands. So when we have 5 rubber bands, that's telling us that our x value is 5. So we're going to take that 5 and plug it in and replace x with 5. So we have 7.464 times 5 plus 25.333. And when we type that into our calculator, we get a distance of 62.653 centimeters. So one of the groups later found the measurement for 5 rubber bands was 64 centimeters. Good job, pretty close. Was that prediction from number 2, the prediction that we had right above of 62.653, too high, too low, and how far off was it? So it looks like our prediction of 62 was, in fact, too low. Just a bit too low, though, not too far. It was too low. And we can figure out how far off by just subtracting. So we'll take 64 and subtract the 62.653. And we can see that our value there, our predicted distance, was 1.397 centimeters too low. And let's make sure we can spell correctly. So we want to predict the distance that Barbie would travel if the group uses 20 rubber bands. So if that group is using 20 rubber bands, that tells us our new x value is 20 rubber bands. So let's go figure that out. So we'll go back to our equation, our predicted y hat, that will be 7.64 times the number of rubber bands, 20, plus 25.333. And we will predict, once we type that into our calculator, that she will travel 173.613 centimeters. What we have done here is we have done an extrapolation. So this word extrapolation tells us is when we find a value, a predicted value from a number based on something outside of the values we use to create this equation. So we got this equation from numbers between 0 and 7. So 20 is very far outside of that range. So we're extrapolating our data to a value that's outside of the prediction. So because that value is outside of the values we're given, we are less trustworthy of this number, because x equals 20 is further out of the range we use to create the equation. It still probably should be pretty trustworthy, because our R value, our correlation value that we talked about last class, was so strong. It was nearly perfect. So it's still going to be trustworthy, but because that x is 20 is so far outside of our range of values that we started with for x, it's a little bit less trustworthy. Our y-intercept, remember our y-intercepts are when x is 0. So for 0 rubber bands, our y-intercept is going to be that value given to us. So we're given our slope and then our y-intercept in our equation. So our y-intercept is 25.333. And then it means that when we used 0 rubber bands, x equals 0, the predicted distance traveled is about 25.333 centimeters. We can figure out our slope of the equation is in that part of the equation as well. So that's going to be 7.464. And what that slope tells us is that for when we add one rubber band, so when x increases by 1, in this case, x is our rubber bands, the predicted distance traveled by Barbie increases, because it's positive, by that slope of 7.464 centimeters. So it increases because our slope is positive, and there is our slope value, m. So I'm going to pause a little bit, and we're going to jump to the second part of 9.2, and we're going to talk about some of that other stuff that we saw on the scatter plot, residuals. In the meantime, hit pause. You'll be able to go try the check for understanding for this first part. I'll see you on the other side. And we're back a couple pages later talking about how many iPhones will be sold, still thinking about correlation and lines of best fit or least square regression lines. And we're going to add to that a little bit of residuals. So we have the type of iPhone that was developed and looks like one every year for about 8 years here. And then the units sold in millions. So 500,000, a million, 1.7 million, so on and so forth. Use the calculator. I actually use Staplet, and I'll show you in a second, to create a scatter plot with the year as the explanatory variable and the units sold as the response variable, and sketch the scatter plot in the space above. Here is the scatter plot. So you may notice the x-axis I actually have as years after 2007. So I start at 0 for 2007, and then every year after that. So I have that right there as well. And first we're going to talk about form. So the form of the distribution, does it look like it's linear? Maybe we can insert a line right over it and try and see how linear it is. I don't really think it's perfectly linear, obviously not like our last question that we looked at. If I move this, maybe there's some above, some below, but it does maybe look like it's a little curved. So let me just try and sketch that out too. It might look like it's even a little curved like that. Maybe exponential, maybe quadratic. I don't know yet. But really what we're trying to figure out is it linear? And it does not look linear. So we're going to write down there that this does not look linear. So the distribution does not, looks non-linear, we can say. We'll use the calculator or Staplet to find the least squares regression line. We're going to write the equation below and graph it on our scatter plot above. I should probably go and erase those other lines I've already drawn on there as well. So I'm going to erase a few things, and we're going to hope that we can make Staplet draw the line on here. So let's take a look at the correlation, 956. That's not too bad. And there is our equation there. We got that y hat. You may notice that it's written a little backwards from how I wrote the last one. Let me just grab that equation right there, so I can toss that in. And we should also be able to see, there we go, our line on the graph as well. So I'm going to go right in our least squares regression line real quick. So we do have y hat is negative 1.3978 plus 1.605. And I'm going to recopy my scatter plot over as well. And we'll be back to look at some of these graphs as well below. There we are. Beautiful scatter plots. No need to guess or make any intervals on our own. All right, so we're going to use the least squares regression line to calculate the residual. There's a new keyword for today, that word residual, and we're going to interpret that residual. So basically what we are looking at here is we're going to figure out how far away from the actual number of units sold the equation predicts. So what we can do is we can take this predicted units sold. So in this first year, 2007, 500,000 units were sold, and what was predicted to be sold was about negative 1.4. So then how far off from the actual units sold is that? We can do the actual minus the predicted. So 0.5 subtract the negative 1.4 actually gives us a positive 1.9. In 2008, 1 million units were sold. Our calculator equation tells us that we expect 0.21 or 210,000 units to be sold. So we'll take 1 minus that 0.21, and that gives us 0.79. Instead of making you watch me do the rest of that subtraction and filling in, I'm going to pause it. And when I come back, it'll all be filled in, and then you can pause it and write it all in. Magically, all the values have now showed up. So we can see that we start with some positive residuals, we get into some negative residuals, and then we get back into positive residuals. So let's graph that on the axes below, and that's going to be called a residual plot. So we'll just plot those points. So in 2007, we're about at 1.9, and then 0.79, and then negative 0.81, negative there, negative back down here. Then we started back to positive, and then smaller positive and bigger positive, approximately like that. And then it wants us to identify which were greater than predicted, which were less than predicted. So we can see that here and here, our actual was greater. And then below, our actual was less. So is that regression line a good fit for the data? It does have an R value that's pretty strong. However, when we look at this residual plot, what we might be able to see sketched out is a kind of quadratic shape there. So that'll tell us that it is probably not linear at all. So we shouldn't use a linear regression on this problem because we're getting a pattern that's not random. We should see something random to be able to have a good linear regression. So because the residual plot looks more like a quadratic, a regression line is not a good fit. the distribution is nonlinear. So you're going to get a chance to practice this on your calculator as well using stat edit and finding those values. I happen to like statlet.com because it throws that line on there for you. It gives you the points. It does all the axes, intervals for us, and it also gives us a beautiful residual plot as well that we didn't have to sketch ourselves. It also gives us a fun dot plot of all the residuals as well. It gives us a correlation with one click of a button. It also tells us S and R squared, which your teachers can get into later. Now you should go ahead and try the check for understanding on the next page, and we'll see you in a couple of lessons.